own. But I know that majority of the stuff we would kind of need to know would have been calculation, so we focused mainly on that. And we went through all of that, and the stuff that we covered were stuff that we got tested on, except for the frequency modulation. I wasn't sure if we were getting it, and because we spent so much time on the amplitude modulation, I wasn't able to go through frequency modulation. So I can tell, well, at least for me, I struggled specifically with that section because focusing mostly on amplitude modulation. Did you hear that, sir?
I heard you loud and clear, Mr. Stewart. I was saying as you heard Miss Henry say, a lot of the information. You see, one thing that tells me a lot about the students is to see whether or not how much actually students are reading based on what they actually say. So are watching in this case and reading, because a lot of the stuff have been posted. I come every week asking students to fill me in on anything that they would not have learned and understand, or give me feedback. I really rarely get anything of that sort. But the information was there. A matter of fact, I'm gonna share something with you now, which will help you. So you would have learned and pretty much everything based on what was posted in terms of FM. If there anything that you do not understand, here's the opportunity to let me know. I'm going to share part of a video that I'm going to post just in order for you guys to get even additional clarification on something. And then for the remainder of the class, we're going to be focusing on what? On noise. So 1 second, I'm going to post a video, all right? And we're going to watch together, and then you can provide your comments afterwards, okay? Are you guys seeing my screen?
Yes, sir.
We're gonna watch this starting from here, and I will stop it when necessary. Please make notes, and we're gonna come back to it, all right?
Amplitude of a modulating signal decreases, the frequency of a carrier signal also decreases. Hence, its time period increases and the carrier signal expands.
Sorry, I can alter the volume, please. It's kind of low.
Now, let's see the concept of frequency deviation. The amount by which the carrier frequency varies from its unmodulated value is called as deviation, represented as delta. The deviation is proportional to the instantaneous voltage of the modulating signal. The modulating signal is given as xt equals Em cos 2 pi Fm into t. The carrier signal is given as Ec equals A into cos omega c into t plus phi. The instantaneous frequency of a Fm wave is given as Fit equals Fc plus Kf into xt. Substituting the value of xt, we get the equation Fit equals Fc plus delta into cos 2 pi Fm into t, where delta is the deviation. Minimum frequency of the modulated wave is given as F minimum equals Fc minus delta, and maximum frequency is given as F maximum equals Fc plus delta. The bandwidth of FM wave is calculated as BW equals 2 into number of sidebands. It can also be obtained using Carson's rules as BW equals 2 into maximum deviation plus maximum frequency. Consider an example now. In a FM system, if the maximum value of deviation is 90 kHz and the maximum modulating frequency is 15 kHz, then calculate the deviation ratio and bandwidth of the system using Carson's rule. We have maximum deviation equal to 90 kHz and maximum modulation frequency equals 15 kHz. We need to find the deviation ratio and system bandwidth. For that, we use the formula D equals delta max upon F max and bandwidth equals 2 into max deviation plus max frequency. The formula for max deviation is D equals delta max upon F max. Substituting the values, we get D equals 6 kHz. According to Carson's rule, bandwidth equals 2 into max deviation plus max frequency. Substituting the values, we get bandwidth equals 210 kHz. Now let's study FM transmitter. FM also uses the crystal oscillator to
Was that too fast for you guys? All right, question?
Yes, sir, a bit too fast.
All right, so I'm going to post a link in the classroom. But generally, this information would have been shared already with you in regards to FM wave. The only thing that is new and wasn't brought out here was pretty much how. Okay, so I posted in the chat for you, Mr. Stewart and et al. I'm gonna share it in the Google Classroom as well. Now, there is more than one way to find a bandwidth. Carson's rule in finding bandwidth for FM wave is an approximation. A more exact science is using what is called a Basal function. Mathematically, at your level, you don't necessarily need to know how to come up with a Basal function. However, you need to understand how to use the Basal function table, which again is something that was posted as one of the questions, but I could have been posted as one of the question, but I didn't because of the fact that we didn't do the table as yet. Now, let's go back to my whiteboard. So Mr. Brown, right?
Yes, sir.
Of course, you'll have enough time that you can watch it in your own time.
Okay, thanks.
But simple what it's showing you is how it is that you can actually find certain properties from defining FM wave, finding the maximum deviation and maximum frequency, what those are, and how you calculate the bandwidth using Carson's rule. We have done AM transmitter, AM receiver. We're going to go back to Basal function table, but I want you to have a look at the FM. Okay. All right, guys, so here we are. I'm going to show you quickly how the FM transmitter works. Remember now the whole objective is mixing two frequency, higher frequency carriers signal frequency with information signal, or what they call a modulating signal frequency. So let's finish looking at this because we have looked at AM transmitter. So let's look at how the FM transmitter generally works.
To generate the carrier signal. This carrier is then applied to a phase modulator.
Let's start it off.
Equals 2 into max deviation plus max frequency. Substituting the values, we get bandwidth equals 210 kilohertz. Now let's study FM transmitter. FM also uses the crystal oscillator to generate the carrier signal. This carrier is then applied to a phase modulator. The modulating signal is applied to the audio equalizer, which is basically an integrator. The output of an equalizer is applied to the audio amplifier. Phase modulator accepts the carrier and the modulating signal and produces the frequency modulated signal at the output. The carrier frequency and modulating index are then raised by passing it through frequency multipliers. The carrier frequency is then raised by using a mixer, and then FC and MF are raised to a required high level. The FM signal is then passed through a Class C amplifier to raise its power. The advantages and disadvantages and applications of frequency modulation are as follows. Advantages of frequency modulation. Improved noise immunity. Entire transmitted signal is useful. Covers larger area with the same amount of transmitted power. Transmitted power remains constant. Disadvantages. Very large bandwidth is required. FM transmitters and receivers are very complex. Application of FM, radio broadcasting such as Vivid Bharati, Radio Mirchi, etc. Sound broadcasting and TV. Satellite communication. Seriously, pay attention. This is important. Next, we will study about a very important concept, super heterodyne receiver. The process...
So we're not going to look at super heterodyne receiver right now because we have looked at it already. Agree?
Yes, sir.
Okay. So pretty much you have the FM transmitter mixing two signal, a high frequency signal through the use of a crystal oscillator with a lower frequency signal. Audio, usually it's a audio signal. Mixing it through a mixer, do some filtering, do some amplification, and send it through a Class C amplifier to the antenna for transmission. Importantly, ladies and gentlemen, the advantages and disadvantages of your FM wave. Any question?
No, sir, that part was pretty self-explanatory.
Nice.
So remind me one thing though. What did it say for? It mentioned something about power. I think that was one of the advantages. Remind me of that, please. For the frequency mode. Hello. Hello. Sorry, I'm not hearing you. If you're talking.
Oh, I'm sorry. I was talking about my mic was mute.
Oh,
Yes,
if you were
that's
listening.
Chad.
I was saying it had mentioned one, I think it was an advantage, one of the advantages being something about power transmitted. I don't quite remember what it was. Will you remind me, please? Your mic is muted again, by the way.
All right, there we go. That's better. All right. What happened is that when you transmit as compared to AM signal, right? What happened is that remember we said that when we're transmitting AM signal, one thing that we do is that we mix two signal, we use the power to transmit the signal as far as possible. Now remember, in transmitting we could use the same power to transmit the AM signal and FM signal. But which one will actually be more advantageous to transmit? Because of the fact that the amplitude of the AM signal, right, in voltage, the amplitude is increasing, right, as the signal is amplitude modulated. It's increasing and decreasing. So it means that we're going to be using more power, because remember, power is V times?
V times the I.
Good. So it means that as the amplitude increase, V, it means that we're going to be requiring more power to transmit this the same signal, right? As compared to FM, where FM, as far as I'm concerned, you're using the same amplitude, right?
Yes, sir.
The amplitude is constant. You're not increasing the amplitude, so therefore you're using.
Oh, it means your power should be constant then if your voltage is constant.
Which allows you, generally, it's not really constant, but it has its fluctuation, as everything does. But it will not fluctuate, or the main concentration of the fluctuation in power will not be as pronounced as that of AM. So it means that you can use more, you can use the same power to transmit an FM signal at a further distance as compared.
Further distance steadier as well.
Yes.
All right. So with the frequency modulation, the signal being transmitted, is it a case where since the power is more or less consistent, allowing it to go further distances, is it that the signal is in a sense clearer or more profound?
Okay.
So you muted yourself again.
Yeah, I keep doing that, don't I? I remember that I for the first couple of weeks of this class, we spoke about some things. Yeah. One of them is that the frequency of a signal determines the amount of interference it will encounter. Lower frequencies, such as AM frequencies, usually tend, and to some extent FM frequency, but AM in particular, it tends to, because the frequency is so low, tend to travel around obstacles and objects. So the frequency of an FM wave, because it's a little bit higher than AM, it will face more obstacles. So what happens is that even though it requires less power to transmit the same information, you gotta have to think about intervening obstacles that will affect your FM signal. And that is why in Jamaica, which is a very hilly terrain, it has a lot of hills and valleys. When persons are transmitting for radio station on FM, on the FM band, what they will do is to try to transmit the signal from the studio. So you have a high, and towers are high up on the studio. The antennas are high on the towers, but they'll tend to transmit above obstacle directly towards antennas that are usually placed up on some hills, like Cooper's Hill or oh Lord, I don't remember some of the places. Hatley in Manchester. You tend to send the signals up to the hill at a particular frequency, higher than the frequency that would be used for listenership. And then that antenna up on the hill will reconvert the signal to the 88 megahertz to 108 megahertz frequency band. And then it transmits the signal from the hill down pretty much in an omnidirectional way. And it will reach more people than if you try to transmit the signal from, let's say, for example, Power or Zip, that have their studios usually in a low, dense populated area, area FM. So what is done is that you try to transfer the signal to the hill and then have the hill retransfer the signal at FM 88 to 108 megahertz band down back to the general population. At that rate, FM signal will avoid a lot of the obstacles, which you don't necessarily have to do for FM, because FM signal, AM, my apologies, AM signal, because of the lower frequency, higher wavelength, they'll tend to bend around object, mountain sides, and so on. So they'll still travel at long distances. The only challenge with AM signal is that they are going to now be experiencing interference, because noise amplitude and AM signal amplitude are easily mixed together to for the signal to be distorted. So there's always a trade-off between how you use and the frequency of operation. But there's something that you guys have to understand, and I keep saying this, that frequency is a premium. You cannot just operate at any frequency, because frequencies of operation for any signal, AM, FM, PM, or any other type of transmission, microwave, radar, all of those have to be governed, and those are governed in Jamaica by the Spectrum Management Authority. So not because of the fact that you see that your signal strength is weak, if you're transmitting, let's say IRFM, and you want to transmit to more on point. But your listenership in more on point say, hey, listen, I'm not hearing my signal too well from IRFM. IRFM can I just say, okay, I'm going to increase my power, or I'm going to increase my frequency. It has to get the approval from the Spectrum Management Authority to buy more sensitive or utilize more sensitive transmitters, or to place the transmitters at more suitable locations so as not to interfere with other users of the same FM frequency range. So I don't know if that explains what any clearer, Chad, what you're asking.
That's everything good, man. Hear me?
Okay, good. All right, so I want to move on. One other piece of info before. 1 second again.
Sir?
Yes, I'm going to share another video. Just 1 second.
Okay.
All right, guys, I'm going to share with you now this video on the Basal function table. Now, the Basal function table, well, the Basal function is a mathematical tool used to calculate, to do the analysis of how it is that you can find the frequency band or the frequency spectrum of an FM modulated wave. So then when you mix two signals, higher frequency signal, which is a carrier, and a lower frequency signal, which is a modulating signal, based on the resulting mixture, what would be the total bandwidth of the signal? Mathematically, as I said, you do not necessarily need to know. This will actually show you, give you an idea, but what is more important is how do you use the math to then do the calculation of the Basal function. It's about 10 minutes or so video. So I'm gonna start now, and you can ask any question. I can stop anytime that you are that you have any questions. Okay. All right, here we go.
Okay.
Hello friends, welcome back to this video on analog communication. In this video, we are going to see the properties of the Basal function, which we have already introduced in my previous
feedback.
video.
I'm not sure what's happening.
So in my
Yeah,
previous
yeah,
video, I
okay.
was talking about the wide band F.
So I think both of them might, yeah, both something. I think both of your names must, yeah, no play.
Yeah, everybody has to make sure
So
the
in my
mic
wide band FM, the modulated signal was represented as AC summation n is equal to minus infinity to infinity Jn beta cos omega c plus n omega mt. So this is my Basal function. I introduced the frequency spectrum of the modulated signal as well. The frequency spectrum was looking like this. So I introduced one of the properties to discuss the frequency spectrum in my previous video as well. So here we'll see in detail what are all the properties of the Basal function. So as you can see from the chart, the Basal function's value depend upon the value of n and the value of beta. So first we have to see what is the beta. So let's suppose from the chart you can see if the beta is 0 and n is 0, the value of j, the Basal function, would be 1. You can see it from the graph. Now you can deduce the conclusion if you see all the values from the chart.
All right. I just want to interject here. To go back, look at the chart that she actually has up. That's what's called a Basal function table. You're going to be all the mathematics that she had done and calculated. All of this is captured in one table for ease of use. You do not need to understand the math at this stage, but how it is that you use. What does J, what does beta, and what N represents. And in the table, if you pay attention to the table, you'll see. So for example, she said that if certain values are 0, then the Basal function value would be a certain value, which is 1. So let's have a look again at what she... Yes, Ms. Henry?
Sir, for
You have gone. I'm not hearing you at all, Ms. Henry.
oh, for the carrier, sir, that is in alright, when you find the index, right, and we look at the carrier that we should have on our Basal function graph, sir, or chart. The negative values are it is that one that is inverted in the negative quadrant right there, down there.
Yes, we're going to speak to that. I'm going to tell you what that actually means, all right? I want to first and foremost let you get a grasp of as to what is happening in the table per modulation index, all right? That's the first thing I want you to understand from the Basal function table. All right? Okay. So let's go. Let me mute my mic. So what I'm simply saying, ladies and gentlemen, is that all of this, even add values for n, is what you'll work. This is a mathematical expression for the frequencies of two mixed signal. So while beta with the modulation index, what you're going to find is that you're going to have different J values for which, and the J values are going to be representing the amplitude of the modulated signal. So, for example, if your modulation index, looking at the table right here, if your modulation index, and this first column speaks to your modulation index for the FM wave. If the modulation index is 0, it simply means that there was no modulation. Agree?
Yes,
Yes,
sir.
sir.
Agree. Sorry,
Right.
on the journal. Okay.
Okay.
So there's no modulation. So what happens is that when there's no modulation that takes place in a frequency modulated wave, the resultant FM wave is just going to be the carrier, because there's no signal that is actually changing the frequency of the carrier. So that's why I say on the J, 0, J1, J2, J3, J4, here, J's would be representing the amplitude of the carrier, and then N, which we're going to talk about next, N, it determines the number of significant sidebands. So you notice, if you notice something, the numbers of sideband based on the modulation index increases, but their values that you're going to multiply, because these values are what you multiply the amplitude of the carrier wave by. These values are going to multiply the amplitude of the carrier wave by. But if you notice something, the amplitude gets smaller and smaller and smaller and smaller and smaller and smaller, which simply means that the amount of significant sidebands that you have, they're contributing, the higher the modulation index, they contribute to the overall signal, but their contribution becomes less and less and less, to the point where after a certain, so for example, if your modulation index was 0.5, you'll multiply J naught. J naught is always your carrier. You multiply the carrier of that frequency modulated wave by 0.94, and with a modulation index of 0.5, you have 2 significant side frequencies. No more. Everything else here is not important. All right, because they are not contributing much to the overall signal. It's like having, think about Fourier again. You know, you have a fundamental frequency, and then you have sidebands. But as the sidebands increases, their amplitude reduces.
Yes, sir.
All right, and it means that if they reduce, that they're really contributing less and less to the overall composite signal that makes up the Fourier transform of the signal. All right. So let's continue watching. I just wanted to bring that to your attention. Let me go back and mute my mic before I start again.
That the zeroth value, the J0 beta, you can see from the graph that when N is 0, I can see all the values in that column, and I can deduce that it contains the significant portion of the amplitude. So it is the largest number. After that, the value continuously decrease. So if I see all the values, I can deduce one more conclusion, that all the values are real for every value of N and for every value of beta. So nowhere in the chart you can see any imaginary number. So J and beta is always real for all N and beta. So when I was drawing this frequency spectrum representation, for that what I can do, I had to plot this in frequency domain. So what I did, I took the frequency spectrum of cos omega c plus n omega mt, because this is a real number, it's a number, it's also constant, AC is constant. So now frequency spectrum will depend upon cos, and the frequency spectrum of cos was AC by 2 del omega plus omega c plus del omega minus omega c. So this is the frequency spectrum representation of cos omega. So now I plotted the values of the del functions here, but here it is multiplied by different Basel function. So here it was multiplied with j1 beta, so n was 1 here, but here it was multiplied by j minus 1 beta. So to find out the value of the Basel function at the negative portion of n, so this formula is used. So the negative value of n into minus 1 raised to power n is equal to positive value of n's Basel function. So the j and beta represents the value of the Basel function at positive n. This represents the value of the Basel function at negative n. So when I multiply it with minus 1 raised to power n, I'll get the j and beta. So it's the relation between this positive and the negative part. So I can deduce the relation for even n and odd n. So when I say n is even, so this minus 1 raised to power even would be 1. So now j n beta would be equal to j minus n beta. So if I need to find out j minus n beta, it would be directly equal to j n beta. Now for odd n, so here
Miss Henry, you had asked a question earlier on. I don't know if you're seeing your answer. Miss Henry?
Well, Mr. Top, based on the question Miss Henry asked, I was trying to get it right there, but I don't know if it's because of the dialect of the Indian culture or so.
All she's saying is that, and think about it. Think about it. Really and truly, even when you get minus values in the table, so you say minus values, the values that you see in the table, you're going to multiply those values. Those values are going to be used to multiply the amplitude of the carrier. Remember now, when you have a frequency modulated wave, the amplitude of the carrier is not something that is of great importance, but it's the frequency of the carrier that's going to be changing. Agree?
Yes, sir.
However,
Yes, sir.
from Basel function, they found that the amplitude is going to be affected ever so slightly, but yes, it's still going to be affected. Remember, amplitude is always a voltage, right? The amplitude of the signal is going to be
Yes, sir.
right. What do we know about negative voltage?
Negative voltage. What about it flowing in the complete opposite direction? Or the potential difference between it and a point is the negative?
Negative voltage just simply means that the point of where you're assuming to be your reference point is really opposite to what you assume. So,
That's what I said.
yeah, so therefore, the magnitude remains the same. So as far as magnitude is concerned, a negative voltage and a positive voltage are identical. It just simply means that where you assume your reference is not where your reference really is. That is why you would get a negative voltage. But in terms of magnitude, they're the same. So in other words, do not see a negative voltage and think that because it's at say it is reflected as a negative voltage, it will not have the same effect as a positive voltage. It will have the exact same effect. It will shock you, it will kill you, it will do whatever it needs to do as a positive voltage, okay? So if you go back to the chart that she has here, what she's simply saying is, listen, wherever I say a minus value, the minus value actually is going to equal to the same as the positive value in terms of voltage. It's just that it's going to be of a value that is multiplied by the coefficient. The coefficient multiplies the amplitude. The coefficient value in the table is going to multiply the amplitude of the carrier. And we'll see a little later what that means.
N is odd. So for n is equal to odd, I'll put this power to be odd. So when the power is odd, this minus 1 will be minus 1 to the power odd would be minus 1 outcome. So j and beta would be minus of j minus n beta, or I can write j minus n beta is equal to minus of j n beta. So this is the reason why I plotted the j1 beta in the upside and j minus 1 beta in the downside. So it is equal to minus of j1 beta. So now I can see from the graph how I can plot the values of different values of j for different n and different beta. So I can find out for different minus n as well. So now coming to the next property. So if I am considering my modulation index to be small, so then only these properties would be applicable. So when the modulation index is small, so beta is small, so now that time j and beta, the Basal function can be represented as b by 2 raised to power n upon n factorial. So now from here we can deduce various values of j. So now if I consider the value of beta to be very small, so from the graph you can see when the value of beta is 0, j naught of 0 is 0, j naught of 0 is 1. You can see from the graph. Now j naught of 1 you can see it is also nearly equal to 1. So j naught of beta for the small values of beta, it is nearly equal to 1. You can see it directly from the graph. So now coming to the next property, j1 beta is nearly equal to beta by 2. So now put the value of 0 here. When I put the value of 0, so now beta was 0. So when it is 0 raised to power n, I'll represent it as 1, and n factorial, 0 factorial is 1. So j naught 0 is 1. Now I'll put the value j1. So n is 1 here. So 0 raised to power beta by 2 raised to power 0 was 1. Similarly, if I put 1, so it is beta by 2 raised to power 1 upon n factorial. 1 factorial would be 1. So it is beta by 2. So now similarly, if I put large n, so at the large n, this n factorial would be very large, and beta, because beta is very small, beta is small, so beta by 2 would be small, and if I took the nth power of a small value, it would be a small number, and if it is divided by n factorial, I'll get 0. So from the graph also you can see, if I increase the value of beta, then only, or the modulation index, then only I'll get the side bands. So from here you can see, if I have 0 beta and 0 n, so that time I have only one side band. So here I don't have any upper side band and lower side band. So this is just one signal which is represented. After that, I have two signals. For the one signal, I have the lower sideband as well. So now you can see if I am increasing beta, then only my sidebands would increase. So now from here we can deduce a conclusion that the bandwidth would depend upon the modulation index. In the narrow band frequency modulation, what I said, that if the modulation index is less, then only it is narrow band FM. So from here also you can see that if beta is less, then we don't have many sidebands, and obviously because we don't have sidebands, the bandwidth spectrum would be less. So now I hope you are very clear up to this term. So now this property would be used when we will discuss the power of the wideband frequency modulated signal. So this property is that, so summation n is equal to minus infinity to infinity Basal function square is equal to 1. So now the beta is same and I am changing the value of n. So now you can see from the row, if I take the every element of the row and I square the element, if I add them, now take any row, add the square of the every element, you will get 1. So we'll use this property in the power calculation as well. So now we deduce these conclusions that for small beta, only J naught and J1 beta are significant. You can see it from the chart, and I have already explained it in the narrow band FM as well, that if I have less beta, the modulation index is less, the information is contained in the upper sideband only. So I have one sideband only here. So now the next conclusion is that in the spectrum, the amplitude contains the information. So here you can see the amplitude is J naught beta. Here it's the function of J1 beta, J2 beta. So the Basal function is containing the information. So from here we can deduce the conclusion in the spectrum. So here we are talking about the spectrum. If I talk about the time domain, so in the time domain, the frequency is containing the information, but in the spectrum, the amplitude is containing the information. So here I'll conclude my session on the properties of Basal function. I hope you are clear with the properties of Basal function. If you still have any doubt, you can put the doubt in the comment and I'll try to resolve it as soon as possible. I hope you like this video. If you like it, share it with your friends, subscribe the channel and
whatever Indian. All right.
Mr. Tarp, I guess you have to interpret now, sir.
Okay. A very, very simple interpretation. I'm gonna show you something. I'm gonna show you something to make it very, very, very simple. See my screen?
Yes, sir.
So we're not hearing anything.
I don't know why I keep muting myself tonight. All right, let's go back. All right. So what I was saying is that the frequency modulated wave can be represented as the carrier signal amplitude cos the carrier signal frequency, angular frequency, that is going to be affected or added to by the complete modulating signal or the information signal. How much the carrier will change from its original position to where the modulating signal is going to take it is directly proportional to, in this case, M, which is going to be the deviation factor. So let's say that this is a carrier frequency, FC. When it's frequency modulated, the carrier frequency is going to change that way or in that way. So we would say that it's deviated by some function delta, right? Delta F. So the carrier, because of the modulating signal, is going to cause the carrier frequency. So looking at the frequency alone of the carrier is going to change, frequency is going to change in this direction and in that direction based again on the, remember the amplitude of the modulating signal is going to cause the carrier to change, right? How much it changes is what is right here, which is your deviation factor M. Okay? Maximum deviation, positive way and negative way. So this is going to be total, the maximum or total deviation based on the carrier frequency and the modulating signal rather. It causes the carrier to change in both directions. In other words, if you look at, let's see another way to look at it. And again, this is, again, general people is posted. Another way to look at it. Graphically, I wanted to see if I see another way. Okay. All right. It's not on this. But this is what I'm saying is the signal will move. The frequency will move. The carrier frequency will move in both directions based on the modulating signal acting upon it. This expression mathematically can be broken down into, so what's here? What's here? Right here. Can be broken down, can be represented by this function. And this function, if you notice, is the same thing. What it is called this alpha. And of course, this is M cos beta. That's all I'm doing. What's in bracket here, which is your frequency modulation, right? Is represented by this. Now, this mathematically can be represented by a Basal function, which is this. That's a Basal function identity expression mathematically. Again, as I said to you, ladies and gentlemen, you do not need to know the maths, which is what she was going through, and which is what all of this is going through, right? The Basal function. Now, what you get from the Basal function is a couple of things. This expression here can be rewritten as this, where we're looking at odd and even values for n. So you notice that this says n pi over 2. If pi is even, sorry, if n is even, this value changes. And if n is odd, the value again changes, right? So a half a pi is different from pi. That's what this is saying. So this expression is going to yield value of pi that are going to be negative, not pi, sorry, value of n that are going to give you, when you work it out, pi over 2, this expression is going to give you this function, these functions. Now, all of this, ladies and gentlemen, this is all that you need to know. All of this is one expression and it's not finished, it's continuing. All right? What are the values? We know what, all of this is multiplied, by the way, by VC, which is the amplitude of the carrier. So whatever is being calculated. So what I'm saying is that all of this is one big expression. It's just that this is minus, which comes on here, and let's continue. And then this continues is a plus, which continues here. So all of that continues one big expression, which is all going to be multiplied by the VC. What is VC again?
Amplitude.
The amplitude of the carrier. So, all right. What does J0? What is J0? What is J1? What is J2? What is J3? Well, we don't go to J2. Well, what does all of that mean? That is explained right here. So, MT is the frequency modulated wave, which is what we have here. That's a frequency modulated wave. Can be expressed as this big expression, which is the Basal function identity expression. Okay? Now, M, as you can see, is a modulation index for FM, the modulation index, which she called beta in our expression just now. J0 is a carrier component of the wave. So you notice, if you look at this, change the color a little. If you look at this part of it, you notice that this portion, ladies and gentlemen, will represent just the carrier. You see that?
Yes, sir.
Oh, good. So this is representing the carrier. So when you expand this, it would be VC times J naught of M cos omega CT. That's a carrier. So all the J0 component is just a component of the carrier.
Sir, VC what is a negative voltage? I'm just
VC?
trying to rationalize. Yeah, I'm just trying to rationalize. So you get minus right out there below in the next line.
Okay, let's go one at a time. So what we're saying is that VC is VC that is here. That doesn't change. It's the same VC here. So this VC multiplies everything. Okay? So if we should take VC out and just do the expansion of what's here, what's here could be expressed as this here. And what's here is, when you expand it mathematically, it can be expressed as a Basal function identity. You know trig identity? Well, we also have Basal function identity. This is what it looks like. The Basal function identity can be expanded to greater values based on what the value of n is. Okay? So, we put back VC. So VC was here. We can put back VC outside this because all that we're doing is just what's inside the bracket here. So we can put back our VC here. Okay? So this is what is done right here, equation 728. VC comes here, and the rest of it is your Basal function expansion. Now notice that this is still in N. So when we start to put values for N, that is what makes the expansion all this big thing. And it continues. If you notice the dotted line, it continues. So if we had a fourth term and a fifth term and a sixth term, it would continue. What I'm saying is that this function shows you some clear things. First of all, always be mindful that VC multiplies everything that is inside the bracket, because that's what is happening from here. VC multiply everything that is summed. Okay? So here we go. The first thing that you're going to get is, when you expand this, is that you're going to get, okay, so let n be 0. So if we let n in this expression be 0, then it means that this will be 0 and this will be 0. Agree?
Yeah.
So 0 times anything is what?
0.
Okay. So it means that this term would go and this term would go and leave with what? Just this term. So that's all that you would have left when n is 0. Yeah? N is just a value, right? That's a number that goes 1, 2, 3, 4, 5. So what we're saying is that when n is 0, the only thing that you have from this expression is just this. And this, as you can see, clearly is just a carrier, which tells you that if you do not have any modulation, the only thing you're going to have is just a carrier wave, which makes sense. So when n is 0, only the carrier alone you have. So everything else. But when n becomes 1, when n becomes 1, what are we going to have? We're going to have the 0 term plus, put 1 inside here, jn, j1, m, which is your modulation index, cos omega ct plus, what is n again? 1, right? So 1 times omega m plus n is 1. So if n is 1, this is going to leave you with only pi over 2, right? But of course, the expression is not finished. You have to come down here as well. So again, j, this is a minus component now, so j is 1. All this remain the same, except what you're going to have now is that you're going to have a minus instead of plus here, and a minus pi over 2 instead of plus pi over 2. That's when j is 1. That's when n is 1. When n is 2, becomes g, remember? So that's what we're doing now. When n is 2, we have j2 m cos omega ct plus 2 omega what? Omega mt plus 2 over 2. You're going to left with only pi, right? So like you drop asleep, man.
Oh, so yeah, man, just
No, but they are only somewhere so because so you're
What's the
saying
cost?
that as long as n is 1,
Right.
you're going to get minus j1.
No, man. This is the whole you get minus, my friend, is this is a complete expression. This is how Basal function does the expression. That's why you get a minus, not because you're putting in minus values. What we're saying is that this is the identity. Basal function identity is like a trigger identity. But when you start to put values in the identity, then the identity start to expand out because values is like we call it now.
Yeah, I can understand some of the things that you're saying, but I'm just rationalizing it to say that as long as n is 1, the signs are going to change to minus. You move from positive to negative.
Because you can see why. Do you see why?
No.
Okay. All right. Let's look at it.
Yeah, I'm just saying maybe that's how the basic function works. So I just accept it, but I don't really
No, man. No. This is the expression. This is a Basal function expression. But let's look at what happened. Yeah? Put 1 into this expression. This becomes J1. This is where n is. This becomes 1, which is omega t plus omega ct plus omega mt plus pi over 2. Agree?
Yeah.
Okay. The thing is, when you do that, that only speaks to just the upper side band. It's an expression that is expanded and it has 2 side bands. Remember when we look at AM wave, it's the same thing. We saw that you have the carrier. Oops, no, wrong thing. We have the carrier component, which is the first thing I expressed, plus the upper side band. Notice this is omega plus omega c plus omega n, right? And then you're going to have a lower side band for, again, when n is equal 1, which is omega c minus omega m. Okay? And this again becomes minus because of everything being minus. That's the lower side band. And it happens again when n becomes 2. It's the same thing right here. Omega c plus 2 times, and remember n is 2 now, 2 times omega mt, and this is the upper minus, yeah, the lower. But guess why you don't have, see, you don't have minus this time, you have a plus. You know why?
You're going back to upper, you move from lower, going to upper.
No. What's the cos of pi?
The cos of pi, sir?
Yeah. What's the cos of pi?
0. No, pi 180.
That's all I can guess in.
-1.
Okay. -1, right? Okay. What's the cos of pi over 2?
Sure. 1.
1.
1.
0, sir.
No, man, start guessing. Come on, guys. Pi over 2 is 90, you know.
No, I actually calculated it. 0.
0, sir.
All right. So what when we put, look at
0, sir.
Look at this now. When you put, I'm just doing this because of Delroy say no. When you put 2 pi over 2 that becomes what? Just pi, right?
Yeah.
The cos of pi is what?
-1.
Okay. -1.
Yes, sir.
Okay. So you see why it keep changing to minus and then it go change again to plus? Because this now is going to be the cost of for when pi is 2, when pi is 1, sorry, not pi, n. When n is 1 and when n is 2 and when n is 3, you're gonna have them changing because the cost of pi is gonna the cost of pi is gonna cause the coefficient to change its value. That's what's happening there, Roy.
Okay.
You get it?
Yeah.
Okay.
So it doesn't necessarily have to do with because you move from the upper band or the lower band. It's because of the values that you're putting in for.
Yes, and that makes it an upper sideband and a lower sideband. Because if you look at it, you see, this is when n equals 1 from here to here. That's n equals to 1 in the expression. Right? So that's when n equals to 1. This is when n equals to 0. I should use a different color. Because remember, I was putting in values. This is when n equals to 0 in the expression. So when n is 0 in this expression, put n as 0, that goes and that goes, right? So you don't leave with this part of the expression, right? BC, open bracket. And then this is when n is 2. This is when n is 2. So n is 2. This is it. Here to here. Back here. That's when n is 2. And for n equals to whatever more, you put them in. You're going to find that it's going to fluctuate between these two though, because what happens is that you're going to have even odd number for n each time, right? N pi.
All right, so I'm going to ask a quick question. I'm going to try to clear up something in my brain now. When n equals 0, you're dealing with the upper band.
No.
And when n
No. When n is 0, just plug n as 0 in the expression.
Yeah, at that instant, you're dealing with the upper band.
There's no upper band. You have no sideband when n equals 0. When n equals to 0, in this expression, remember this is the expression, you know, we're expanding.
Yeah.
When n equals to 0, this goes. Agree? Because 0 is 0, right? And then when n is 0, this also goes. So all you're left with is just this 0. Yeah, for n, 0 cos omega ct, which tells you that this is really just a carrier. So there's no sidebands at that time.
All right, so when n equal 1 now, you're dealing with the lower band or the upper band.
You have both sidebands. And that's why I circle all of this yellow part, is this part in yellow.
Okay, both sides.
Yes, this is when, from this expression, this is when n is 1. So n being 1, you put n being, again, let me just erase this so that you understand what we're talking about. N being 1, you put n in the expression being 1. So this is going to be 1. So that makes it omega CT plus omega MT, because this is 1, plus
Pi over 2.
pi over 2. Yeah? But that's just going to give you one of the expression. The expression also is going to add. So this is where it adds to it, a minus 1 cos omega minus, and that's it. And that part of it is the lower sideband. This part, because it's minus in, so you know it's the lower sideband, and this is the upper sideband. So each of this part of the expression is going to give you an upper sideband and a lower sideband when J is not equal to 0.
Okay, understood, sir, understood.
Okay. Now, all that really is not even important. What is important is what is happening here. Here, it tells you what M is, which is your modulated wave, FM modulated wave. M is your modulation index. VC is the peak amplitude of the unmodulated carrier, as we know. J0 is the carrier component, because we realize only the carrier component we're going to get when n equal to 0. And then when n equals to 1, we get this in the yellow. And this part in the yellow is the first set of side frequency displayed from the carrier by omega n. And that's why it's only omega n. When n is 2, it's going to be the second set of side frequency displayed from the carrier by 2 omega n. So at the end of the day, that expression, which is why she was talking about the factorial, the Jn part is an expression, a factorial expression, which again for here you don't need to get into. And what eventually, let's read this part of it, because that's what I want to get to. The most important thing I want to get to you guys. After doing all this mathematics up to equation 730, table 7-3 shows the Basal functions of the first kind for several values of modulation index. So remember, each time we change in M, the modulation index can change, can change M as much as we want. We don't know what the modulation index, but it shows for several different modulation index. All right, but once you find a modulation index, that would stay for the entire expression until you find it for a second one. So if you look back at this, if M is 0, which means that there is no modulation, that's going to be right through the whole expression. If M is 1, the modulation index, it's going to be M is 1 right through the entire expression. All right? So what it's saying is that there are several different M values that this table brings you. So if you look at this table, the first thing that this table shows you is your M values, your modulation index. So it shows your modulation index. When the modulation index is 0, then 0.25, then 0.5, then 1, and so on up to 10. So when the modulation index is 0, and you put that modulation index being 0 into this expression, ladies and gentlemen, when a modulation index is 0, when you do that, what you end up with is nothing. All this goes, you're left with only this part of it. Carrier, and it says that you have no sidebands. That's what this is saying. When the modulation is 0, there's no significant side frequency. So all of these are missing. No significant side frequencies. However, when your modulation index move from 0 to 0.25, you're going to have the J1 is going to be, J0, which is what? the part that affect your carrier. So these are your carrier values. This is how the carrier values are going to be affected in terms of their amplitude.
But when the modulated index is 0, J naught is 1.
Yes, which simply means that if you have no modulation index, if you have no modulation index is 0. It means that you don't have no modulation. You don't have no modulation. The only thing you have is just a carrier. That's what it tells. That's what this is telling you. But as soon as you start to have modulation, what will happen is that the carrier amplitude is going to be affected as well as the significance. So at 0.25 modulation index, yeah, you're going to have the carrier being multiplied, whatever the carrier value is, VC, that's going to be multiplied by 0.98. And how many significants? So the rest of this speaks to how many significant side frequency you're going to have. J1, J2, J up to J whatever. Speaks to side frequency pairs. I notice I said pairs because we realize from this expression that you're going to have a side frequency pair for each of these values. J1, you're going to have the upper and the lower. For J2, you have the upper and the lower. So that's why it's a pair, okay? When, through an example, you see it better. When the modulation index is, let's say, 2, the carrier component is going to be multiplied, the carrier voltage is going to multiply by 0.22, and you're going to have 1, 2, 3, 4 sets of side frequency. 4 sets. All right? Now, what does that mean in terms of reality? Through a question, let's look at and see what's happening. For a FM modulator with a modulation index of 1, so right away, we know what the modulation index is. So if we go back to the table, we're talking about modulation index of 1. So this is one we're talking about. Modulation index of 1. It tells us that we have how many sets of side frequencies? We have a carrier component, and then we have 1, 2, 3 sets of side frequencies. Upper and lower. That's the first thing it tells us. Then it says a modulating signal, VM, is given as this. And an unmodulated carrier is given as this. So we know the carrier frequency, and we know the modulating signal frequency. Most important thing. We know that this is going to be the frequency of the modulating wave, or the signal, or the information. And this is going to be FM. And the only reason it's going to be FM is going to be 1,000. Because physically we can see that is the case. Because we know that angular frequency is omega, and omega equals to what? 2 pi. So this is omega m. And omega m equals 2 pi fm. So the 2 pi here, so it means that this must be fm. Similarly, and again, for those who did the test last week, you should be able to see this easily. This will be the carrier. This is the amplitude of the carrier. So this would be, in our case, VC. That's the amplitude of the carrier. Right here. And then in bracket would be the frequency of the carrier, the angular frequency. We already know that angular frequency is 2 pi omega. Sorry, 2 pi rather, f t. So we have our 2 pi, omega is 2 pi ft. So we say our 2 pi. So we know that this is what is going to represent this portion is what is going to represent our carrier frequency. So this is FM, FC rather. And FC is going to be 500. Well, it's 500 what? 500 K. So it's 500 kilohertz. While this is 1000 hertz. Okay? So be that as it may, they want you to determine the number of sets of significant side frequency that will result from having this frequency modulated wave. We can do that from the graph. Again, with a modulation index of 1, we can go to the graph, not graph, the table rather. We can go to the table and we can determine that this is a modulation index of 1 and it has a carrier plus 1, 2, 3 sets of side frequency. That's what is being asked right here. You must the number of significant side frequency, and in this case it would be 3. What are their amplitude? Now their amplitude, the amplitude of the significant side frequency is going to be VC, which is 10, we already know, multiplied by these values. So that's why we get this, ladies and gentlemen, as our frequency spectrum. We know that this is FC, which is at 500 kilohertz. And we say that 500 kilohertz, we're going to have 2 sets of side frequency, a lower side frequency and an upper side frequency, which means that this is here. It's going to be FC, because we already know it's FC plus FM. And FC, this one, FC minus FM, which gives you the lower.
So, sir, so J, there, so that's essentially said J is 0, is only the carrier frequency.
Yes, man.
So, sir, wait,
go ahead.
So if you give, like in the test where you gave the frequency deviation and the frequency modulation, you'd use that to find the index, right?
Yes.
And then the bandwidth would be FC plus the maximum plus NFM, and then times that by 2. Would that be the bandwidth?
Yes.
Okay.
Oh, so it's okay. So it's the same for both AM and FM. Okay.
Not the same. Similar.
Or similar. Sorry, similar.
Yeah. Because you realize something is going to happen. These values are changing. Remember, the unmodulated amplitude of the carrier was what? 10. That was what was giving the problem, you know. But we realize something, that when you modulate this signal, the J0 value is going to multiply the 10. If you look in the table, the J0 value for a modulation index of 1 is 0.77. See, J0 value, carrier value, is going to be reduced to at a modulation index of 1, it's going to reduce to by 2.77 of what the carrier value was. So that's why it's going to be 0.77 times what the carrier value was again. Carrier voltage?
10.
10. But 10 times 0.77.
7.7.
That is why you have at 500 kilohertz, the amplitude at J naught, which is the carrier, FC, is going to be 0.77 times 10, which is why I get this value. Likewise, the frequency for the pair of sidebands. Remember I say, when for J1, you're going to have two pairs, upper and lower, right? Upper and lower. Remember, this is upper because this is this is FC plus FM. So it's going to be 500. And what FM is again? 500 kilohertz plus 1 pulse hertz, which is 1 kilohertz. So 500 plus 1 is going to be 501 kilohertz. So we know the frequency for J1 for the first sideband. And we know the lower part of it is going to be 500 minus 1. That's why we get 499 hertz. But what's going to be their amplitude? The amplitude is going to be, look back at the table, for a modulation index of 1, J1 value is going to reduce the carrier to 0.44 of what the carrier value was. So therefore, it's 0.44 times 10. Because remember, I say VC is always going to be multiplying, Because remember, VC from our expression was outside of everything. Notice VC is outside of everything that's happening in the bracket, right? So VC times these is going to give you, so VC times in this case J1, but up one for the lower. VC is 10. J1 is based on the modulation index. It's going to be 0.44. So it's going to be 10 times 0.44, which is going to give you in this case 4.4 for the magnitude of the upper sideband and minus 4.44 for the lower. Now, this is the thing that I was talking about earlier. Again, going back to Miss Henry's question. So you notice the magnitude here is going to be what? Minus 0.44 times 10. But because we're talking about voltage, the minus 0.44 is going to still be represented as a modulus, because as far as we're concerned, voltage is going to be voltage, right? And that's why it is going to be 0.44 on the lower side times 10 and 0.44 on the upper side frequency times 10. And there are three side frequencies. So for J2 at modulation index of 1, the carrier frequency is going to be, carrier amplitude is going to be reduced by 0.11. So it's going to be 10 times 0.11, which is going to give 1.1. And the frequency we know, because the frequency in this case is going to be FC minus 2 times FM and FC plus 2 times FM, which is why we have
reduced to 1.11.
All right, you can figure the rest out. That's pretty much what I want you to understand in terms of what's happening here. Now, for the bandwidth of using the Basal function table, you can see clearly if you have a diagram what the bandwidth is. The bandwidth is going to be the upper minus the lower. So in this case, it's going to be 503 kilohertz minus 497 kilohertz, which is going to give you the bandwidth of all to accommodate all of this is going to be a 6 kilohertz bandwidth. You see that? Upper minus lower. That's what bandwidth is. But Mr. Carson mathematically came up with an estimate. And he did it because of the premium of frequency. He said, well, some of the frequencies, as you can see, for example, ladies and gentlemen, a 0.2 volts of the original voltage is not much because the original voltage was 10. So 0.2 is not really much. So if we take off some of these that are contributing really not much to the overall spectrum, we can actually use the frequency much more efficiently. So that's what Mr. Carson came up with. And by extension, these are the formulas, ladies and gentlemen, that you use for FM modulation bandwidth calculation. Okay? Mr. Carson, Basal function says the bandwidth of an FM wave is given as 2 times n. Remember, n is the number of significant sidebands times the frequency of the modulating signal. That's how Mr. Basal function table determines the bandwidth of a system. Let's use that and do our calculation. I show you graphically how to do the calculation, and I'll finish in about 5 minutes or less. So what was n again? So this is 2 times n. What is n? What? How many significant side frequency we had, ladies and gentlemen?
3.
For a modulation index. Right, so for a modulation index of 1, we're going to have 2 times, open bracket, 3. We got 3, right? Cleaned out, go back. See?
Yeah, 3.
For modulation, we don't include the carrier, we include the significant sideband, which is 1, 2, 3. So 3, yeah, times what's the modulating frequency?
1,000.
1,000. So 3 times 1,000 is how much? Oops, 1,000.
3,000.
3,000 times 2 is how much?
6,000.
6K. You see how I got the 6K? Remember graphically I told you it was 6K. Is just 503 minus 497. So mathematically, we can work it out. Plus we can use Mr. Basal function table. No, Mr. Carson used a different expression. He said that the bandwidth is the peak frequency deviation plus the modulating signal frequency, and then multiply that by 2. Now, from what was given, what would have been our peak deviation?
Go back on the graph.
Sure, come on, sir, from what was you know, what?
3,000. 3,000.
No.
Oh.
What's the question?
If we were supposed to use Mr. Carson's method, how would we determine the bandwidth? The bandwidth is determined by this formula for Carson of an FM wave. He says that the bandwidth for FM wave is 2 times the peak frequency deviation plus the modulating signal. Again, I show you guys something. This is a carrier frequency, FC. The modulating signal is going to cause FC to change in that direction and in that direction till it can't change no more. So this is FC, and this from here to where stop is delta F, and the lower side part would be also delta F. Oops, that's delta F. So the peak deviation, not peak to peak, the peak deviation is from here to here. That's a peak deviation. So in our example, for argument's sake, this is a carrier and the peak deviation would be up to here, which is what? 500 minus 503 minus 500, which would be what? Peak deviation would be
3,000, sir.
3K.
What that mean, sir?
Yeah, man. Well, I want you to be sure how you get it. I just don't want you to say it.
Happy.
So that is your peak deviation, delta F. Okay? And that's what Mr. Carson is saying. He says that it's a peak deviation plus the modulating signal frequency. So it would be, we just found this, plus we know what FM is what? 1,000, right? So 1,000 plus 3,000.
1,000.
4,000.
4,000, sorry.
Minus 2 would be 8,000. 8K. That's how he does the calculation. All right? Here's another example.
So I understand the different values that we're getting. One is saying 8,000, one is saying 6,000.
Yes, and that is perfectly fine. What I'm saying is that there are 2 different methods to calculate the frequency, the bandwidth of an FM wave.
Yeah, but one man gets 6 kilohertz and one is getting 8 kilohertz.
All right.
Which one?
Mr. I want to read this. Just that alone tell you something. What does it say?
It has a Carson rule is an approximation. And gives a transmission bandwidth.
And I did say that before. That what happened is, you guys remember I said it before? Carson came up with a mathematical approximation based on the limitation of frequency and the frequency spectrum. He said that he could not afford to use frequency loosely using the Basal function table calculation, where Basal an approximation. It says Carson's rule define a bandwidth that includes approximately 98% of the total power in the modulated wave. So he's using 98% instead of 100% to do an estimation, okay? So there's absolutely nothing wrong. And lastly, look at the last example and you will see how it even tells you more. It says that if you have an FM wave and it has a peak deviation of 10K and a modulating frequency of 10K, so the deviation is 10 and the modulating frequency is 10K. And you know the voltage of the modulating, of the carrier signal. And you know the frequency of the carrier signal. It says that you must find actual minimum bandwidth from the Basal function table, and you must also use Carson's rule to find so 2 rules to find the bandwidth. Now, Basal function, remember, is B equals to what? 2 times see? Basal says it's 2 times N times FM. Okay, based on what we're given here, what is N? Well, the first thing we have to do is to find what the modulation index is. And the modulation index for FM wave is delta F over FM. So that's why the modulation index for FM, I'll say it again, the modulation index for FM wave is delta F over FM. We're given delta F to be 10K, we're given FM to be 10K, so therefore the modulation index is 1, similar to what we did before. The modulation index is 1, and we're using Basal function table. We gotta go back to the table, and it's the same thing we just did, so it's easy for us. With a modulation index of 1, we are gonna have the carrier being 0.77 times the carrier voltage, which is gonna be 7.7 again, because the carrier voltage unmodulated was 10 volts. And again, it's going to be points for the first significant sideband, second significant sideband, and third significant sideband. We can calculate these times 10 volts to give us the voltage that is contributing to the side frequencies. So here, we found that our modulation index is 1. When our modulation index is 1, we know how much significant side frequency is going to have. We know that it's 3 significant side frequencies. So, Basal function says that the bandwidth equals to 2 times N times FM. So, N is the number of significant side frequency, which was 3. FM is 10K. So 3 times 10, that's 30K. And that 30K times 2 give you 60K for the bandwidth using Basal function table. However, Carson, on the other hand, says you don't need to do all of that. All you need to do is just to find delta F plus FM multiplied by 2. So what is delta F? Delta F is given already as 10. What is FM? It's also 10. So it's going to be 10 based on Carson. It's going to be 10 plus 10 times 2. 10 plus 10 is what? 20. 20 times 2.
40.
Okay. So you're going to see that, oops, where am I?
You're right, you're welcome, right?
Right here, right. So you see, this is an approximation using Carson as to 40. See, what Carson did was to say, okay, these two, based on the values that you're given, in terms of how much you're contributing, we can't get rid of those. They're not contributing much. They're not a whole number contribution. So what he did is say, okay, it's going to be from here to here. And that's going to be your bandwidth using Carson's. But Basal function don't make no assumption. It says it's taking everything from here to here. And that's why the bandwidth for, in this case, Basal function is going to be a bit higher than using the Carson approximation method. Any questions?
Approximation burn on the place.
Sir.
Yes, sir.
Yeah. Based on this that I'm seeing, would it therefore mean that the Carson's rule would give you the more useful bandwidth, seeing that the 0.2 volts here on each side for the Basal function would be, what would you say, maybe irrelevant.
It's not irrelevant. It's just that as far as Carson is concerned, it does not necessarily contribute as much in terms of the overall amplitude of the signal, and therefore for taking up so much space on the frequency band, not worth it. And therefore Carson tried to eliminate it.
Okay.
But with the Basal function, they find the bandwidth and use all of that bandwidth.
Sorry, but
there's no approximation. There's utilizing everything.
But as I said, because the frequency is of such a premium, I guess Carson's rule would give you a more economical approach to.
More economical initially, at least. So.
Okay.
But sometimes, especially in the practical world, you're gonna realize that approximation never worked out yet.
Okay.
It's approximation burn on the place.
People who standardize things will not use approximate method. Am I clear?
Yes, sir.
Good. Any further questions? Don't feel anyway, post it on the Google Classroom, all right?
Yes, sir. See if I can post it earlier than usual. I'll go class today.
Okay.
Sir?
Yes, sir.
I sent you an email describing the situation that I'm currently in. You can take a look at it and provide an feedback.
I will do that.
All right, thank you, sir.
Okay. All right, if there are no further questions, I'd like to leave it there for tonight.
Yes, sir. Mine as well.
Next time we meet, I'm going to again share, because we're going to look at noise. That was the intention. We're going to look at noise and how noise affects the communication system. So we'll have looked at AM, FM, the different components, so transmitter, receiver. We look at the reason for the AM and FM and the mathematical analysis. Now we finish with those, we're going to look at communication.
Sir, 1%, sir. before you go. As it regards to lab, sir, what's the latest update? You have anything planned as yet, or what's the way forward? Given the current situation,
Miss Henry.
Yes, sir.
You still work out of the lab?
Repeat that, sir.
Do you still work out of the lab?
Yes, I do, sir. But face-to-face sessions are cancelled.
Right.
And in regards to the live session, the live meeting that was kept by the Prime Minister.
All right, I'm gonna supersede the Prime Minister and tell him to open back everywhere. But anyway, I'm just kidding. Obviously, it means that we won't be able to do that. What we're probably gonna have to do is I'm gonna post something up for you guys to do. In terms of, still, it's not lab, but it's lab related. It's practical related, I should say. But this is not something that you're gonna have to do in a lab scenario, but something that you can do on your own. But it's just not feasible right now. But I made that.
Okay, and Mr. Torp, sorry to interject on your point. What if you have not done any lab yet?
Well, the same is going to apply. We're operating right now in trying times. We just have to work with the trying times to try the best we can. Because
wait, sir, how long will wait till we can just go to the labs again?
That's what you that's the worst thing in the trying time not to look.
It is trying. Because nobody, the people, you see, people behave themselves and adhere to the protocol. It's a bit much. But the Jamaicans people in the US, remember all this thing that came to the US, the president and things. It's a hoax.
So, sir, those who do the labs already, that just cancel.
No, man, not cancel. We want to see what you do. That don't affect. It's that it don't affect what have been done already. It affect going forward. So I would cancel the one I do already.
Okay, sir. I want to ask you something, sir. Wait, that's right. Sir. Yes. For devices 2, the test is for everybody tomorrow? Because I have class during the Thursday time.
What was your question you just asked, young man?
No, I was just asking, sir, for devices 2, if the test is for everybody tomorrow, because I have class during that time.
Okay.
We thought, but the test is for everybody. But we thought separately because I know some people definitely can't make it to the course.
I can't make it.
Sir, remember to send me the class code for DSP here, sir.
All right, let me do that now. And I'm out, guys. Have a good night.
Yes, sir. You too.
Yes, sir. I'm going to check email for my Kiana Block.
All right, Mr. Block. I know the email. I just how to respond to it is something that because your thing has gotten the faculty attention, Mr. Block.
Okay, sir.
All right. Have a good night.
Sir, in my case, wait, sir. So wait, I'll go in my case. So.
What is your case, Javon?
Him said talk
the device is
here. Answer that, brother.
Javon, may you talk differently? All right, you have class tomorrow, so we have our test for you differently.
Okay.
All right. Take care, guys. Have a good night.
Bless up yourself, sir.